Hello and welcome to my channel. In this video I will show you how to use the Laplace transform. We will solve a very basic example of differential equation. This equation we already analyzed in a previous video and link to it I will put in the description. Okay, so the differential equation is dy over dt equal to a times y. Okay, so it's the simplest differential equation ever. We have the derivative of function which is proportional to a function itself by the proportionality constant a. And now we would like to use a Laplace transform to solve this equation. Okay, so first of all the notation. If we have the f of t is a function of time and we make the Laplace transform of this function, then we obtain the f, capital F of s. That's just a notation. Okay, but now most important thing is how do we change this domain from time to s? S is a Laplace variable. This change of domain led us to change the differential dependential to algebraic dependencies. What I mean is we change differential equation to algebraic equation. Then we can perform some operations to solve this equation, and once we have our solution as a function of s, then we can retransform it. I mean we can go back from the s domain to the time domain. Okay, and this idea I will show you on this simple example. So in our case, our function y of t will be denoted after the Laplace transform as a y of s. Okay, so how to perform this change of domain? So the Laplace transform is defined in this way. So this is the integration from 0 to infinity from the function f of t. This is a function we would like to transform, multiplied by e to the power of minus s times t. This is a, of course. Okay, dt. And when we perform this integration and when we apply those limits, you can see that t will disappear and we only have left s, the Laplace variable. Okay, so from the previous video we know that the function which is a solution of this equation is e to the a times t. Okay, and there should be also an initial condition, but it's not important for now. Okay, so this function now I will transform to the s domain, and later when we solve this equation in s domain we will see that we will obtain a transform of this function. F of t is e to the a t, and now when I transform it, so f of s is an integral from 0 to infinity for my function, which is e to the a times t, times this part, e to the minus s times t. over dt, of course. Okay, and this is particularly simple to compute. I can do this, that it is e to the a minus s times t dt. Okay, and this is really simple integration. To integrate this, we just need to divide this function by this part in here, in the exponent. Okay, I will not explain it now, but it is really simple to check. Okay, so we have e to the a minus s times t, okay, over the a minus s, okay, and limits 0 and infinite. Okay, and now we need to make an assumption about the s. What I mean, we can have three situations when a is bigger than s, then this all of this expression is bigger than 0, I mean, and it implies that this denominator goes upward to infinity. Okay, in other situation, when s is bigger than a, we have this expression negative, so here is a minus in front of t, so we have the situation when it actually decreases to the 0 when the times go to infinity. Okay, and this will be the situation we will analyze further. And of course, this third situation is when a approaches s, and in this situation all of this expression approaches infinity, because the value of denominator approaches 0. And such a situation when a approaches s is called a pool, so the answer blows up to infinity. Okay, and it is really interesting thing in the case of automatic regulations, but it's not important for us for now. Okay, so now we make an assumption s is bigger than a, and this applies this result. Okay, so when I apply the limit and the time approaches infinity, all of this approaches 0. Okay, and the lower limit is 0, so when I put a 0 here, I've got 1 in here. So what I have is minus, because I subtract the lower limit from the upper limit, and the upper limit is 0, so I have minus and the lower limit, and the lower limit is 1 over a minus s, which is 1 over s minus a. Okay, and this is Laplace transform of this function here. Okay, so now let's go and transform this part of our equation. So now the idea is that my f of t is actually dy over dt, and the y is of course a function of time. Okay, it's not important what is this function, but the important is that I have now differentiation here. Okay, differentiation of this function. Okay, so still I need to apply my Laplace transform by its definition. Okay, and what to do with it now? Now we need to apply the integration by parts. So I will use the formula for it without explanation, because this is a topic for another video. Okay, so this is the formula for integration by parts. What is the meaning of this? The integration by parts let me to remove the derivative from here and move it to the other function, because I've got two functions in here. This is one and this is the other. Okay, so using integration by parts, I can remove the differentiation from this function and put it here. So now I've got y of t, my function, and the derivative of this function, which is minus s times e to the minus st. Okay, but to have this equality in here, okay, I need also to add this term, and the limits are subjected to this term. Okay, same limits as here in the integration. So we have the minus here and minus here, and we also have integration from 0 to infinity y of t e to the minus st dt, which is by definition the Laplace transform of y of t, means y of s. Okay, this is particularly this expression. Okay, in here. And we have also this s, but here we integrate over dt, so s we can treat as a constant here, so it goes out. So we have actually s in here. What is the conclusion? The conclusion is that operation of differentiation in a time domain is a multiplication in a Laplace domain. So in domain of s, we just multiply y of s by s, but it's not over. Still we have this part here. So let's think about it a bit. If we now impose the limits, if time approaches infinity, this is minus, so all of this approaches 0. Okay, so in the infinity it is 0, and now I only impose the lower limit, which is 0, so all of this in this manner is 1 when t is 0, so I only have y of t when t is 0, so I have y of t 0, which is my initial condition. Okay, so, and I also have a minus sign here. Why? Because I subtract the lower limit from the upper one. So I have minus initial condition. Okay, the interesting thing is that you can notice that differentiation in a Laplace domain is represented by the multiplication by s. And because differentiation and integration are the opposite operations, now you understand why the integration in a Laplace domain is represented by the dividing by s. And when we will work with Simulink, which I will provide a lot of videos about it in the near future, you will see why, and you will understand why the integrators are denoted in like this in Simulink. And now you also know why the initial conditions are provided here in the integrators block. So now we are ready to solve our differential equation, which is this one, by using the Laplace transform. And now we know that it is in a Laplace domain y of s times s minus y of 0, which is just initial condition, and when I move it here, I also have a times y of s, which is just the transform of this function. Okay, and all of this is equal to 0. Okay, and as you can see here, this is just a Laplace transform of my function, which is here. Okay, this is this Laplace transform. So now, making the inverse Laplace transform, we just find the description of our function in a time domain. So y of t is equal to, this is just a number, an initial condition, y of 0 times the inverse transform of it, with just the function of time e to the at, which is this solution you already know and understand from the previous video when we solve the same equation with a very intuitive way of understanding without any sophisticated math. But this is really important to understand the Laplace transform properly, because it is a lot of applications of it, especially in case of theory of control and automatic regulations, which I will also provide the videos about it. Okay, so if you found it useful, give a thumbs up, give a sub. Okay, see you soon in the next video.